In this video, I'm going to talk about the stress concentration factor. So when a material has a defect in it, such as a notch or a crack, for example, stress concentrations can occur. And we can use a sketch to see how this happens. So let's say that we have something with a notch in it, and we apply a uniaxial stress in this direction. The stress, you can imagine, is sort of carried by these stress lines. And at the end of the sample, these stress lines are uniformly distributed. But because the cross-sectional area is reduced at the presence of the notch, then the stress is increased there. So these lines should stay within the sample, but you see the idea that the stress is getting concentrated around the presence of the notch. So the stress is concentrated here. And you can kind of imagine that this is a bit like a magnetic field. So the force is being transmitted through these force lines, but at the center point here, right here, the cross-sectional area is smaller, and so they're forced to come together. And so this leads to the presence of a stress concentration. Now, we can try to quantify this stress concentration through the stress concentration factor. This figure here helps us to see how the stress concentration factor comes about and can be defined. Right here is this notch, and what we see in the figure is that immediately at the notch, the stress is increased, and it's the highest right by the notch, and then it decreases as we move toward the center of the specimen, and then increases as we come back over here. This symbol, this is sort of mislabeled in the text. Really, this should say sigma NSS. So that's the net section stress, and it's just defined as the force that's being applied divided by the cross-sectional area at the notch. And it's in terms of this sigma NSS, so the stress essentially that's acting across this area, and we compare that to the sigma max. So sort of how much is the stress elevated here as compared to at the center. So the stress concentration factor is defined as K sub T, and this is sigma max divided by sigma NSS. So KT, this is our stress concentration factor. Stress concentration factor. And it's comparing this sigma max, so how much is it increased at the notch as compared to that net section stress. That gives us our stress concentration factor. Now, depending on the geometry of the notch or of the crack, because this stress concentration can also arise from a crack or a pore inside of the specimen, depending on that geometry, that determines that value of sigma max. So let's try to look at how sigma max depends on the geometry of the crack or the notch or the flaw. So let's assume that we have an elliptical defect in the middle of our sample, and I've drawn it with these wavy lines here around the edges to sort of say that this is a infinitely large, or not infinitely large sample, but it's really large compared to this flaw. So in this drawing, the flaw is about half as wide as the whole specimen, but this model doesn't apply if that's the case. So we have to assume that this sample is very big and that this ellipse is rather small as compared to it. And the ellipse has the features that it's 2a in length and it is 2b in height. And on the basis of those parameters, we can give an equation for sigma max. And so sigma max is equal to sigma, which is the applied stress over the whole sample, times 1 plus 2 A over B. So 1 plus 2 A over B. One thing we can see from this is that as the ellipse is flattened, then B gets very small and sigma max gets very high. So as the ellipse is flattened, so that would mean it's becoming a little bit more crack-like and a little bit less sort of notch or pore-like. Sigma max gets very high. And this is how a higher stress concentration can be generated. Let's consider then the case of a very flat crack, and we can define then a radius of curvature, and that depends on the geometry as b squared over a. So this is the radius of curvature, essentially of the crack tip, or of the notch tip. And so we can then write sigma max is equal to sigma times 1 plus 2 square root of A over rho. Oops. And this is approximately equal to 2 times sigma square root of A over rho in the case where rho is much, much less than A. Okay, so this is the approximation that we can make for sigma max. In the case when this is essentially a very sharp crack as compared to the length of the crack. And so another way that we can define the stress concentration factor. So the first way we did it was in terms of the maximum stress as compared to that next section stress. Another way that we can do that definition is as 2 times the square root A over that crack tip radius. So let's look at an example regarding what the magnitude of KT might be. So we're going to assume here that we have a specimen loaded in uniaxial tension. There is a pore in the center of radius equal to A. And so we can essentially look at the stress along this line. And so we want to know, as a function of position, what is that stress? So the radius of curvature is equal to A, and sigma max is equal to the stress times 1 plus 2, the square root of A over A. And so that is just equal to 3 times sigma. So the maximum stress that we find is 3 times sigma. And so at the edges far away, that stress is sigma. But right here at the edge, that stress is equal to 3 times sigma. And the stress sort of falls away like this. And the same thing is true over on this side. So right next to that hole, the stress level is 3 times sigma, and at the edge it's equal to sigma. And I should point out, this is really the best case scenario, right? So this is the largest that radius of curvature could be. Any other case will make this term higher here. So this is the best case scenario. So we have seen in this video then what the stress concentration factor is and how it arises due to those force lines being concentrated either around a crack tip or at a notch in a specimen.